For decades, farmers have been told that yield comes down to three main nutrients: nitrogen, phosphorus, and potassium. Every season, millions of dollars are spent across North America applying these fertilizers, carefully calculated per acre, often with sophisticated equipment and detailed soil tests. And yet, something strange keeps happening. Two farms apply nearly identical fertilizer programs. One field produces strong, dark green crops and excellent yields. The other struggles with pale leaves, weak root systems, and disappointing harvest numbers. Same crop, same weather, similar fertilizer programs, but completely different results. Most people blame the usual suspects: weather variability, seed genetics, bad timing, or simply bad luck. But agronomy has a less comfortable explanation. Sometimes the problem is not the fertilizer. Sometimes the problem is the foundation underneath everything. And that foundation is soil pH. If soil fertility were a machine, pH would be the master control switch. It quietly determines whether nutrients remain available to crops or become chemically locked in the soil where plants cannot access them. In other words, a field can contain plenty of nutrients, but if the pH is wrong, those nutrients might as well not exist. To understand why this happens, we need to step back and look at the basic chemistry of soil. Soil pH is simply a measurement of acidity or alkalinity, on a scale from 0 to 14. Most agricultural soils fall somewhere between pH 4.5 and pH 8.0. A value of 7 is considered neutral. Values below 7 are acidic, and values above 7 are alkaline. At first glance, the difference between pH 5.5 and pH 6.5 might seem small. It is only one number. But in soil chemistry, that difference represents a massive shift in how nutrients behave. At lower pH levels, certain elements become much more active in the soil. Aluminum and manganese, for example, begin to dissolve more readily. In small amounts these elements are harmless, but at higher concentrations they can become toxic to plant roots. Aluminum toxicity is one of the most common hidden problems in acidic soils. When aluminum levels rise, root growth becomes restricted. Roots thicken, branch less, and struggle to explore the soil profile. A crop with a limited root system cannot efficiently capture water or nutrients, even if those nutrients are present. At the same time, several critical nutrients begin to disappear from plant availability. Phosphorus is particularly sensitive to soil pH. In acidic soils, phosphorus reacts with aluminum and iron to form compounds that plants cannot absorb. The fertilizer is technically still in the soil, but chemically trapped. It is the agricultural equivalent of locking money inside a safe and losing the key. Potassium efficiency also drops in strongly acidic conditions, and calcium and magnesium levels often decline as well. Over time, soil structure can degrade as these base cations are depleted. Farmers then respond in the most logical way possible. They apply more fertilizer, more phosphorus, more potassium, more nitrogen, but if the pH remains incorrect, much of that investment continues to be restricted by the same chemical limitations. The result is a cycle that many farms unknowingly repeat for years. Lower pH reduces nutrient availability. Fertilizer efficiency drops. More fertilizer is applied to compensate. Costs increase, but yields do not improve proportionally. This is why many agronomists refer to soil pH as the single most important soil property influencing crop productivity. Before nitrogen efficiency can improve, before phosphorus uptake can increase, before roots can explore deeper soil layers, the pH environment must allow those processes to function. Think of soil pH as the operating system of your field. You can install the best software in the world, but if the operating system is unstable, nothing performs the way it should. Across the Midwest and much of North America, the optimal pH range for most major row crops falls between roughly 6.2 and 6.8. Within this window, nutrient availability is near its peak, microbial activity is strong, and root systems can expand freely through the soil. Corn, soybeans, and wheat all perform well in this zone, although each crop has slightly different preferences. Corn generally performs best between pH 6.0 and 6.8. Soybeans often prefer slightly higher conditions, closer to pH 6.3 to 7.0. Wheat is somewhat more tolerant of acidity but still benefits from pH levels above 6.0. When soils fall significantly below these levels, a cascade of problems begins to unfold. Root restriction, reduced nutrient uptake, lower fertilizer efficiency. And yet, many farmers rarely think about pH except during occasional lime applications. In fact, on many farms, lime decisions are made based on habit rather than precise measurement. A field might receive lime every 4 or 5 years simply because that is the way it has always been done. Neighbors apply similar rates. Local recommendations remain unchanged, but modern soil science has revealed something important. Soil pH is rarely uniform across an entire field. Even in relatively small fields, pH levels can vary dramatically from one area to another. Differences in soil type, organic matter, drainage patterns, and historical fertilizer use all contribute to these variations. One part of the field might already be near the optimal pH. Another section may be significantly more acidic. When lime is applied uniformly across the entire field, two things often happen simultaneously. Some areas receive more lime than they need. Other areas receive far too little. The result is uneven correction and inconsistent crop performance across the field. Today, precision agriculture tools allow farmers to map pH variation in remarkable detail. Grid soil sampling, GPS mapping, and variable rate application technology make it possible to correct pH exactly where it is needed. But before exploring those solutions, we need to confront a deeper question. Because for many farms, the issue is not just uneven pH. It is something more surprising. Sometimes the pH numbers farmers rely on are not telling the full story. And that misunderstanding begins with the difference between active pH and buffer pH. Understanding that distinction is where the real science of lime management begins. And it is also where many fertilizer dollars are quietly lost. A sample is taken from the field, sent to a laboratory, and a few days later the results arrive: organic matter, phosphorus levels, potassium levels, and somewhere near the top of the page, a simple number labeled soil pH. For many growers, that number becomes the reference point for every lime decision that follows. If the pH is low, lime is applied. If the pH looks acceptable, nothing is done. At first glance, this seems perfectly reasonable. Soil pH is supposed to tell us how acidic the soil is. If the number improves after lime application, the problem should be solved. But there is an important detail hidden behind that single number. What most farmers see on their soil test is something called active pH. Active pH measures the acidity of the soil solution. In other words, it measures the concentration of hydrogen ions currently floating in the water surrounding soil particles. This is the environment directly touching plant roots. Active pH is important because it tells us the immediate chemical conditions a crop experiences. But active pH does not tell us how resistant the soil is to change. And that resistance is controlled by something called the soil's buffer capacity. Imagine two different soils, both testing at pH 5.8. On paper, they appear identical, but in reality they may behave completely differently. The first soil might be a sandy soil with low organic matter and low clay content. These soils have very little buffering capacity. Their pH can change quickly with relatively small lime applications. The second soil might be a heavy clay soil with high organic matter. This soil can hold a large reserve of acidity attached to its clay and organic matter particles. Changing its pH requires far more lime. Both soils show the same active pH number, but the amount of lime required to correct them could be dramatically different. This is where buffer pH becomes critical. Buffer pH measures the soil's reserve acidity. It estimates how much acidity is stored on the exchange sites of soil particles and how strongly that acidity resists change. In simple terms, buffer pH tells us how hard the soil will fight against lime correction. Without this information, lime recommendations become little more than educated guesses. Many laboratories include buffer pH in their soil test reports, but not all farmers pay attention to it. In some cases, the number appears on the report without much explanation. In other cases, the test may not be run at all unless specifically requested. When buffer pH is ignored, lime recommendations can be wildly inaccurate. A field with strong buffering capacity may receive far too little lime, meaning the pH barely improves. The farmer spends money, spreads tons of material across the field, and a year later the soil test shows almost no change. Frustration sets in. The farmer assumes lime simply takes longer to work, or that the application was ineffective. But the real issue may be that the soil required far more lime than the original estimate suggested. The opposite situation can also occur. Fields with very low buffering capacity may receive more lime than necessary. Over-liming can push soil pH too high, which introduces its own set of problems. At higher pH levels, micronutrients such as zinc, manganese, and iron become less available to plants. Crops may begin to show deficiency symptoms even when those nutrients are technically present in the soil. This is why professional agronomists rarely make lime recommendations using active pH alone. They combine active pH, buffer pH, and soil texture to estimate the true lime requirement. And when these factors are calculated correctly, the difference in lime requirement can be dramatic. Consider a simple example. Two fields both test at pH 5.8. Field A has low buffering capacity and may require only 1 ton of lime per acre to reach the target pH. Field B has high buffering capacity and may require 3 tons per acre to achieve the same result. If the farmer applies 1 ton uniformly to both fields, Field A may correct perfectly while Field B barely changes. One field improves. The other continues to struggle with the same hidden acidity problems. Multiply this scenario across hundreds or thousands of acres, and the financial consequences become clear. Large fertilizer budgets are spent each year attempting to push yields higher. But if pH correction is incomplete, the soil continues to restrict nutrient availability. The crop cannot fully use what is being applied. This is why agronomists often describe pH management as one of the highest return investments in crop production. Correcting pH does not add new nutrients to the soil in the same way fertilizer does. Instead, it unlocks the nutrients that are already there. Phosphorus becomes more available, potassium uptake improves, root systems expand more freely. Microbial activity increases, improving nutrient cycling and organic matter breakdown. In many cases, farmers see yield improvements after pH correction even when fertilizer rates remain unchanged. It is one of the rare situations in agriculture where improving the soil environment can increase productivity without dramatically increasing input costs. But this brings us to another question farmers often ask. If lime is so important, why do some fields respond quickly while others seem to change slowly? The answer lies not only in soil chemistry, but also in the physical characteristics of the lime itself. Not all lime materials behave the same once they reach the field. Some react quickly, others may take years to fully influence soil pH, and the difference between them is measured by a number that many farmers rarely examine closely. That number is called ENM, effective neutralizing material. Understanding that number can mean the difference between lime that begins working within months, and lime that takes several seasons to reach its full effect. And once farmers begin looking at ENM instead of just price per ton, the economics of lime management start to look very different. When farmers compare lime prices, the conversation almost always begins with a simple question. How much per ton? It is an understandable instinct. Agriculture is a business built on margins, and input costs matter. When two lime suppliers offer material at different prices, the cheaper option often appears to be the smarter decision. But in the case of agricultural lime, price per ton can be one of the most misleading numbers in the entire soil fertility program. Because not all lime has the same ability to neutralize soil acidity. Two materials may look nearly identical when spread across a field. Both may come from limestone quarries. Both may even carry similar labels. Yet their real effectiveness can be dramatically different. To understand why, we need to look at two physical properties that determine how lime actually performs in the soil. The first is chemical purity. Agricultural lime works because it contains calcium carbonate, a compound that reacts with acidity in the soil and neutralizes it. The higher the concentration of calcium carbonate, the greater the neutralizing power of the material. This property is measured using something called calcium carbonate equivalent, often abbreviated as CCE. Pure calcium carbonate has a CCE of 100%. Some lime sources may test slightly above that value if they contain magnesium carbonate as well, as is the case with dolomitic limestone. Other materials may contain impurities such as clay, sand, or other minerals that reduce their neutralizing power. A lime source with a CCE of 80% simply does not contain as much acid neutralizing material per ton as one with a CCE of 95%. But chemical purity is only part of the story. The second factor, and often the more important one in the short term, is particle size. Lime reacts with soil acidity only when its particles come into contact with the soil solution. The smaller the particles, the greater the surface area exposed to chemical reactions. Fine particles react quickly. Large particles react slowly. This is why lime is typically ground before being sold. Grinding increases surface area, allowing the material to begin neutralizing acidity much faster. However, grinding limestone requires energy and processing. The finer the material, the more expensive it becomes to produce. As a result, some lime products contain a large proportion of coarse particles. These larger particles may still eventually react with soil acidity, but the process can take years. From a long-term perspective, those particles still have value. From a short-term crop production perspective, their impact may be minimal. This is where the concept of effective neutralizing material, or ENM, becomes extremely useful. ENM combines both chemical purity and particle size into a single measurement that estimates how effective a lime product will be at correcting soil acidity. In simple terms, ENM tells you how much of the material will actually begin working within a reasonable time frame after application. Two lime products might both cost $30 per ton, but if one has an ENM value significantly higher than the other, it will neutralize more acidity per ton applied. That means fewer tons are needed to achieve the same pH correction. Suddenly the more expensive lime may actually be the better investment. Unfortunately, many farmers never examine the ENM value when purchasing lime. They look at the price per ton. They look at hauling distance. They may ask neighbors which supplier they prefer. But the number that most directly determines lime effectiveness is often buried in technical documentation few people read. Let's consider a simple example. Suppose a field requires 2 tons of lime per acre based on soil test recommendations. Supplier A sells lime for $25 per ton with an ENM rating of 70%. Supplier B sells lime for $35 per ton with an ENM rating of 95%. At first glance, supplier A appears to offer the better deal. But because the material is less effective, the field may require closer to 3 tons per acre to achieve the same pH correction. Once transportation and application costs are included, the cheaper lime may end up costing more overall while still delivering slower results. This is not a rare situation. Across many farming regions, lime quality varies widely between sources. Differences in quarry geology, grinding equipment, and processing standards all influence the final product. Yet because lime is often viewed as a basic commodity rather than a precision input, these differences are sometimes overlooked. The irony is that lime is one of the few inputs capable of improving the efficiency of nearly every other input used on the farm. When soil pH moves closer to the optimal range, fertilizer efficiency increases. Root systems grow deeper and more aggressively. Microbial activity becomes more active, helping break down organic matter and release nutrients naturally stored in the soil. The entire biological and chemical system of the soil begins functioning more effectively. In that sense, lime is not simply a correction tool. It is an efficiency multiplier. A well-corrected soil allows farmers to capture more value from every pound of fertilizer they apply. And when fertilizer prices are high, that efficiency becomes incredibly valuable. But even with high-quality lime and correct application rates, another challenge remains. Soil pH does not change instantly. Lime reactions take time. In some cases, farmers apply lime and expect immediate improvements the following season. When the results appear slower than expected, they begin to question whether the application worked. Understanding how quickly lime actually reacts in soil is critical for setting realistic expectations. Because the timeline of lime effectiveness depends on several factors: soil moisture, temperature, particle size, and the way the lime is applied and incorporated into the soil. Some of these factors can accelerate pH correction significantly. Others can slow the process to a crawl. And once we understand how those factors interact, the timing of lime applications begins to look very different from what many farmers have traditionally believed. One of the most common questions farmers ask after applying lime is simple: how long until this actually fixes the pH? It is a fair question. Lime is not cheap, spreading it across hundreds or thousands of acres requires time and fuel, and every farmer wants to know when that investment will begin paying off. Unfortunately, the answer is not as simple as many people expect. Lime does not behave like fertilizer. When nitrogen fertilizer is applied, the crop may respond within days. Leaves become greener, growth accelerates, and the effect is visible within the same season. Lime works very differently. Instead of feeding the crop directly, lime gradually changes the chemical environment of the soil. And chemistry takes time. The reaction begins when lime particles dissolve in soil moisture. Once dissolved, calcium carbonate reacts with hydrogen ions, which are responsible for soil acidity. This reaction neutralizes acidity and gradually raises the soil pH. But the speed of this process depends on several important factors. The first is particle size, which we discussed earlier. Fine lime particles dissolve more quickly because they have greater surface area exposed to soil moisture. Coarse particles, on the other hand, dissolve much more slowly. Some large lime particles may remain in the soil for years before fully reacting. This is why finely ground lime often produces faster pH correction than coarser materials. The second factor is soil moisture. Lime reactions occur in the soil solution, which means water is essential. In dry conditions, lime particles remain relatively inactive. In regions where soils stay moist through much of the growing season, lime can begin reacting relatively quickly. In drier environments, the same material may take longer to show measurable results. The third factor is temperature. Chemical reactions generally move faster in warmer soils. During cold seasons, microbial activity slows and many soil reactions become less active. As a result, lime applied in the fall may react slowly through winter but accelerate again when soil temperatures rise in spring. The fourth factor is soil mixing. When lime remains only on the soil surface, its ability to influence deeper soil layers is limited. Rain and natural soil movement will eventually carry some of the material downward, but the process is slow. In conventional tillage systems, incorporation helps distribute lime throughout the topsoil, allowing it to react more evenly. In no-till systems, lime is often surface applied. Over time it gradually works its way into the soil profile, but the process may take longer to influence deeper root zones. Because of these variables, lime response times can vary significantly. Under favorable conditions with finely ground lime and good soil moisture, measurable pH changes may begin appearing within 6 to 12 months. In other situations, full pH correction may take 2 to 3 years. This timeline sometimes surprises farmers who expect immediate improvements. But once the chemistry begins shifting, the benefits can last for several seasons. Unlike nitrogen fertilizer, which disappears quickly through plant uptake, volatilization, or leaching, lime can continue influencing soil pH for years after application. In many soils, a single lime application may influence pH for 4 to 6 years, depending on crop rotation, fertilizer use, and natural acidification processes. And that natural acidification is an important part of the story. Modern agriculture constantly pushes soils toward acidity. Nitrogen fertilizers, particularly ammonium-based sources, release hydrogen ions during the nitrification process. Over time, this increases soil acidity. Crop removal also contributes. Every harvest removes calcium, magnesium, potassium, and other base cations that help maintain balanced soil chemistry. Rainfall gradually leaches these nutrients downward through the soil profile. Little by little, the soil becomes more acidic. This is why pH correction is not a one-time task. It is an ongoing management process. Fields that are perfectly balanced today will slowly drift toward acidity over time if they are not monitored. That is why regular soil testing remains essential. Most agronomists recommend testing fields every 2 to 3 years, especially in high-yield cropping systems where nutrient removal is significant. With modern precision agriculture tools, farmers can now track pH variation within fields with remarkable detail. Instead of applying lime uniformly across an entire field, variable rate technology allows lime to be applied only where it is needed. Areas that are already near the target pH receive little or no lime. More acidic zones receive higher rates. The result is more precise correction, lower overall lime use, and more consistent soil conditions across the field. In many operations, this approach not only improves soil chemistry but also reduces input costs. And that brings us to one final question. Because once farmers begin correcting pH properly, something interesting happens. Fertilizer suddenly begins working the way it was supposed to all along. Fields that once struggled to reach yield targets begin responding more strongly to the same fertility programs. The soil system becomes more efficient. And when that efficiency improves across hundreds or thousands of acres, the financial impact can be far larger than many farmers expect. Understanding just how much money soil pH can influence is where the real economic story begins. If you found this breakdown helpful, consider subscribing to the channel. Every week we explore the hidden factors that influence farm profitability, from soil chemistry and fertilizer efficiency to the agronomic mistakes that quietly cost farmers thousands. Watch next: the nitrogen leaching lie, the potassium paradox, soil compaction, the silent profit killer.